friends, welcome to video lecture on free undamped single degree of freedom system. Under this, we'll cover conversion of physical system into spring mass system and some numericals. Now let us start with the first physical system. So our ultimate aim is to transfer this physical system into spring mass system, okay, like this one. So here one bar is attached at fixed end, okay, like this one. And when the longitudinal oscillations are given for this system, this will start oscillate about the mean position, okay. So for that, some of the dimensions available with us, so whatever the stiffness available or possessed by this bar, we can just show by this one letter K, okay. We can just straightforward replace this one by spring, and whatever the mass available in the system, we can just show that by M. So this is the physical system. We can show this physical system by this spring mass system like this one. Once we get information regarding this K and M, can get the information regarding the frequency. Now the value of static deflection delta may be found out from the given conditions of the problem. For longitudinal vibrations, it may be obtained by a relation. We know this one, E is nothing but stress divided by strain, or E is nothing but, so what's about the stress? Stress is nothing but here force per, what's about the stress? Force per unit area, okay, like this one. So force we can get in terms of self weight of this divided by cross section area. And what's about this strain? Strain is nothing but the change in deformation or change in length divided by original length. So here we can get delta divided by L. So L goes in numerator. So in this way we can get the relation for this E. E here is nothing but the Young's modulus for the constraint or this rod. Okay. So E is nothing but stress divided by strain, or we can get relation for this E like this one, W divided by A multiplied by L divided by delta. Okay. So what do we get here? WL divided by A into delta. So deflection delta can be get like this one, delta will come here, okay, and E goes in denominator. Okay. So what do we get here? WL divided by A into E. What's about the delta? Delta indicate the static deflection, that is the extension or compression of the constraint or the given bar, okay. So W is nothing but the load attached to the free end of the constraint. What's about the L indicate? L is nothing but the length of the constraint or that particular bar we have considered. E indicate the Young's modulus of the constraint, and A indicate the cross section area of the constraint. So what's about the K? So basic definition for the K, okay, in front of you, force by deflection. So force with us in terms of W and deflection with us in terms of this one, delta, WL divided by A into E. So here once we get the deflection for physical system, okay, can easily get the information regarding this K. So whatever the weight involved in the system and deflection, whatever the force with us, okay, in terms of weight, okay, once you get the information, can easily get the value for the stiffness, and further can get the information regarding the frequency. So in this case, this delta with us, WL divided by AE. So easily you can get this K, W get cancel. So AE divided by L will come for this K. So this is nothing but the relation for which one? Frequency, omega n equals to square root of K by M. So in this case, we know the value for the K. K is nothing but AE divided by L. Just replace this K by AE divided by L. Okay, this term, okay, with us, and M will remain as it is. So omega n equals to, what do we get? AE divided by square root of AE divided by M into L. So this is with us in terms of radian per second, and this is with us in terms of hertz. 1/2 pi square root of AE divided by M into L. When this one, the physical system is subjected to only pull, or when we consider the longitudinal vibration. So in this way we can get the deflection, and then once we get the deflection, easily we can get the value for k. Further we can get the value for omega. Now if we consider the transverse vibration in the system like this one, beam is subjected to transverse vertical force or natural frequency of the free transverse vibration. For that, let us consider the cantilever beam loaded at the free end like this one. So this one mass is attached at the end of this uh, constraint, or say at the beam. Okay, so when we transfer this physical system into spring mass system, so what are the stiffness? Just by this bar we can just show that stiffness by this spring, that is k with us, and whatever the mass is attached at the end of this one, we can just show that mass here like this one. So in this we can transfer the physical system into spring mass system. Now the static deflection, we know the static deflection due to weight of the body. For the this one cantilever beam, delta equals to WL cube divided by 3 into EI. What's about this W? W is nothing but the load at the free end in newtons. So what's about this L? L indicate the length of the shaft or beam in meter. What's about the E indicate? E is nothing but the Young's modulus for the material, the shaft or beam in Newton per meter square. I indicate the moment of inertia of the shaft or beam in meter raised to 4. Okay, so what's about the K? K is nothing but the, as per our previous discussion, force by deflection. So force with us in terms of W, and deflection again in terms of delta. So what's about this delta? Already in case of cantilever beam, we have seen delta is nothing but W divided W into L cube divided by 3 EI. Just replace this delta term by this term. So delta term by this term, W L cube divided by 3 EI. Okay, so here in this case W get cancelled. So what's about the K? K is nothing but the 3 EI divided by L cube. So what's about the omega n? Omega n equals to square root of K by M. So what's about the K? K already with us 3 EI divided by L cube. 3 EI divided by L cube. Mass will remains as it is. Okay. Also this Fn we can get in terms of hertz like this one. This with us in terms of radian per second. Okay. So Fn equals to 1 upon 2 pi square root of 3 EI divided by M into L cube in terms of hertz. Now this is the case of cantilever beam, or when the particular beam is subjected to transverse vibrations. Okay. Next one is nothing but natural frequency of simply supported beam with a central point load W. Okay. So here this one central point load W we have considered here. Now deflection of the beam due to the point load W acting at the center is delta equals to 3 L cube divided by 48 EI. Now as far as concerned with this deflections, already this deflection topic you have studied in case of strength of material. If you get the deflection for any system, you can easily get the value for K, and further we can get the value for the frequency. Now in this case delta with us WL cube divided by 48 into EI. If you compare with the previous one, the 3 EI result with us in case of transverse vibration. Okay, this one like this one, and in this case this result with us for the deflection. We consider the simply supported beam, delta equals to WL cube divided by 48 EI. So here this W is nothing but the load at the center, then L indicate the length of the shaft or beam, E indicate the Young's modulus for the material of the shaft, okay, in Newton per meter square. I indicate the moment of inertia of the shaft or beam. Okay, so what's about the K? Look towards this relation written. Third time we have written the same relation. K equals to force divided by deflection. Force with us in terms of W, and this delta we can get the different for the different cases. So in this case WL cube divided by 48 EI. This relation with us for the delta. So if I substitute here, WW get cancelled. So what do we get here? You can get 48 EI divided by L cube like this. Further, in the next step, we can get omega n equals to square root of k by m. So k with us this term. This term indicate the k. So 48 EI L cube, 48 EI L cube m will remain as it is, and get this relation in terms of radian per second. Okay, and this relation with us in terms of hertz. Now say the problem involving the physical systems. Okay, so here the find the natural frequency of the mass m for the system as shown in figure. Neglect the mass of the cantilever. Study the special case when k equals to infinity and second case when I equals to infinity. The system is given like this one. So cantilever beam is given. At the end of this beam, a spring mass system is attached. So length for this beam with us L, stiffness for the spring with us K, and mass, okay, M with us, along with the displacement X with us here. So you can just see here the physical system. See the equivalent system. Physical system can be converted into equivalent system like this one. So whatever the stiffness for this beam, we can just consider the stiffness K1. So at the end of this one, another spring is connected. Already the stiffness is given for this one as K. This one and this one connected in the series. So whatever the stiffness of this one and this stiffness of the spring with us should be connected in the series. So K1 stiffness we are assumed for the stiffness of this cantilever beam. So K1, and next spring with the stiffness K. So at the end of this one, mass is attached. At last, if I again take the equivalent, the spring, we can just replace both the spring by one equivalent spring. At last, we can get the system like this one, spring mass system. So our target is to get the value for this equivalent stiffness. Okay. So for that, if you look towards this one, the cantilever beam system with us. Okay. So already we have seen while discussion of that cantilever beam case. Okay. Now, in case of cantilever beam, the deflection delta due to some force W acting at its end such that, so what's about the deflection of cantilever beam? So already I have seen delta equals to W L cube divided by 3EI, okay, X, IX, like this one. So what's about this K1? K1 is nothing but here force divided by deflection. So force with us W and deflection with us here. This is the deflection with us WL cube divided by 3EI. Okay. So here WW get cancelled. So we can get a relation for this K1 like this one. 3EI X divided by L cube. So what's about the omega n? Omega n natural frequency you can get with the help of this relation. Square root of K equivalent divided by M. Give equation number 1 for this one. So here if you look towards the actual converted system, okay, in that system the two springs are connected in the series. So when the springs are connected in the series, we know how to do calculations for equivalent stiffness. So equivalent stiffness can be calculated with the help of this relation. 1 upon K equivalent equals to the stiffness for the first spring with us K1, second with us K. So in this way we can get the relation for K equivalent when the strings are connected in the series. Okay. So 1 upon K equivalent equals to 1 upon K1 plus 1 upon K like this. So this one 1 upon K1, already this term calculated by us K1. K1 is here 3EIX divided by L cube. So replace this K1 by this term. Okay. So we can get here 1 upon K equals to, if I substitute the value for this K1 as 3AI divided by L cube. So L cube goes in denominator, in numerator. Okay. So L cube divided by 3AI x plus 1 upon K will remain as it is. So 1 upon K equivalent equals to, so make the base common for this one. So 3AI multiplied by this term, just multiply by this term with this this term, multiply by this term with this term, okay, and just make the base common by multiplying this term with this one, okay. So we can get in this way, k l cube plus 3ei multiply by 1 means here 3ei x divided by this multiply by this one 3ei into k, like this. K equivalent is nothing but the reciprocal of the previous step. So previous step, this one, this with us. Take the reciprocal of this one. K equivalent is nothing but 3eix goes in numerator and this term comes in denominator, like this. So 3eix divided by k l cube plus 3eix, okay, into this one. K will remains here, okay. So what's about the omega n? Omega n is nothing but square root of this indicate the k term, okay, divided by m term. So 3eix into k divided by 3ei this term plus k into l cube divided by this one, m will remains as it is. What's about the frequency in terms of hertz? Only 1 upon 2 pi term is added in the previous formula, okay. So two different cases are given there. Study the special case when k equals to infinity and second case when I equals to infinity. Okay. So see here, when k equals to infinity, if you concentrate on the equation number second, so equation number 2 with us here, equation number second with us, 1 upon k equivalent equals to 1 upon k1 plus 1 upon k. If I substitute the value for k as infinity, here 1 upon k means here 1 upon infinity. 1 upon infinity is 0, okay. So k equivalent must be equals to k1. So in this way you can get the step 1 upon k1 plus this 1 upon k term, this term becomes 0, okay, as the value for k is infinity. So 1 upon infinity must be equals to 0. So k equivalent is nothing but k1. So k1 value already with us. So what's about that k1? K1 is nothing but 3eix divided by l cube. So substitute the value for that k1. K equivalent is nothing but k1. So you can get the omega n equals to square root of 3ei divided by l cube into m. In short, this system is similar to the system as shown in figure number 1. So only at the end of this one, cantilever beam, one mass is attached. So here 1 upon k becomes 0, means here the stiffness for the spring mass, this one, the stiffness for this one becomes 0, means this system is not exist in the system, only the cantilever beam and at the end of this one mass is attached. So in this way you can get the system, only this one cantilever beam and at the end of this one mass is attached. And a second case when I is equals to infinity, okay, second case when I equals to infinity, okay. So this relation already with us, 1 upon k equivalent equals to 1 upon k1 plus 1 upon k. So from equation number 1 already we know k1 is nothing but 3eix divided by l cube. So in this case, when the value for this one k1, this value when becomes infinity, automatically the value for ix is also becomes infinity, okay. So 1 upon k1, when k1 becomes infinity, here ix becomes infinity means here k1 becomes infinity. So k1 infinity, the meaning for this one, 1 upon k1 means 0. So straightforward, what do we get here? This becomes 0, means k equivalent equals to k. When the k equivalent becomes k, means in the system k1 not exist. K1 not exist means in the system only spring mass system exists. This one spring mass system exists. The stiffness produced by this cantilever beam is not exist, means the value for 1 upon k1 here becomes 0. Okay, means we can get k equivalent is nothing but here straightforward k equals to k, and we can get the natural frequency like this one, omega n equals to square root of k by m, which is similar to the system here as shown in figure number 2, spring mass system. The spring possesses stiffness k and having the mass m. Now see the next problem. A rod of circular cross section and of uniform diameter 100 mm is fixed at one end. A disc of mass 500 kg is attached at the other end. Radius of gyration of the disc is 250 mm. Length of the rod is 100 cm. Modulus of elasticity of the rod material is 3 into 10 raised to 5 mega Newton per meter square, and modulus of rigidity is 8 into 10 raised to 4 mega Newton per meter square. Find the frequencies of natural, longitudinal, transverse and torsional vibrations in hertz. Now if you go through this problem carefully, here the diameter of the circular rod is given 100 mm. Okay, convert this into meter. Then mass of the disc is attached at the other end. The mass is given 500 kilogram. Then radius of gyration 250 is given. Then length of the rod is given 100 centimeter. Okay, convert everything into meter. Okay, so here modulus of elasticity is also given. E equals to 3 into 10 raised to 5 mega Newton per meter square. Mega means here multiply by this term by 10 raised to 6 term 6. Okay, so 6 plus 5 11, we can get this way, 3 into 10 raised to 11 Newton per meter square. Similar with this case, modulus of rigidity G equals to 8 into 10 raised to 4 mega Newton per meter square. Mega means here 10 raised to 6. Okay, 6 plus 4 10. So in this we can get the G equals to 8 into 10 raised to 10 Newton per meter square. Now just focus on the longitudinal vibration. In case of longitudinal vibration, so our first aim is to get the value for delta. Once you get the value for delta, easily can get the value for stiffness. So in case of longitudinal vibration, here the deflection delta of the bar having the longitudinal force W along the length L would be given by, already this relation studied by us in the discussion of that conversion of physical system into spring mass system. Okay, so in case of longitudinal vibration, delta equals to WL divided by AE. Okay, then what's about the K? K is nothing but the force divided by deflection. Force with us in terms of W and deflection with us here WL divided by AE. So W divided by WL divided by AE, one W get cancelled, AE goes in numerator. So what we get here, K equals to AE divided by L, like this one. So this is the circular rod with us. For that cross section is nothing but pi by 4 into d square. Diameter with us 0.1 meter. So easily we can get the area of the cross section. So what's about the area? A equals to 7.854 into 10 raised to 3 meter square. So here, if you substitute the value for A, E and L here, so what we get here, can get the value of K. So K you can get here after calculations 2.356 into 10 raised to 9 Newton per meter. So easily you can get the value for omega n is nothing but square root of K by M. K with us 2.356 into 10 raised to 9 divided by 500. After simplification, we can get omega n equals to 2170.804 radian per second, and in terms of hertz, so simply divided by this term 2 pi, what we get, 345.494 hertz. Okay, so this is the answer in case of, if you consider the longitudinal vibrations in the system. Now if you consider the transverse vibration in the system, only change occurs for the deflection. So deflection, we know in the transverse plane, the deflection delta of the bar having a bending force W. So what's about the delta? If I consider the transverse vibration, okay, so already I studied this case with the help of a cantilever beam. Okay, So W L cube divided by 3EIX. This is the relation for delta. What's about the K? K is nothing but W by delta. So W already with us, delta already with us here. The value for delta here, W with us, so W get cancelled. We can get the relation for this K in this way, 3EIX divided by L cube. What's about this IX? IX is nothing but pi by 64 into d raised to 4. What's about the diameter D? D is nothing but the 0.1 into 0.1 raised to 4 will comes here. What's about the I? I is nothing but this term, 4.909 into 10 raised to minus 6 meter raised to 4. So get the value for K. K is nothing but 3EI divided by this one L cube. Substitute the value for I here, E here, L here. Okay, get the value for K. K is nothing but, after doing calculation, 4417864.7 Newton per meter. Now get the value for omega n. Omega n equals to square root of K by M. K already with us. Substitute here. Already the mass term with us, 500 kilogram. So after calculations, we get the value for omega n equals to 93.999 radian per second. So in case of hertz, we can get this way. Just divide this term by 2 pi. We can get 93.999 divided by 2 pi is 14.96 hertz. Okay. Now, if we consider the torsional vibrations, in torsional plane, the torsional stiffness of the rod is given by kT. So kT relation with us, kT equals to Gj divided by L. So what's about the J? J is nothing but pi by 32 into d raised to 4. This indicates the polar moment of inertia. Get the value for J, pi by 32 into d raised to 4 means here 0.1 raised to 4. Get the value for J. Once you get the value for J, get the value for KT. KT is nothing but the Gj divided by L. Okay, from that relation, just substitute the value for every term and get the value for KT. So KT equals to 785398.16 Newton meter per here radian. Okay, what's about the I? I is nothing but the mk square. So radius of gyration already given in the problem. So get the value for I. I is nothing but here 31.5 kg meter square. What's about the omega n? Omega n is nothing but square root of kt by I. Kt, this value already with us, I value already with us. So get the value for omega n. Omega n equals to 158.533 radian per second. Okay, and here we can get the omega frequency in terms of hertz by dividing this term by 2n. Get 25.231 hertz.